Hello friends, in this video lecture we are going to discuss the optimum generation scheduling considering transmission losses. So let us begin. So friends, till now we have discussed what is optimum generation scheduling, and of course in our previous lecture we have discussed transmission losses. Okay, see, we have arrived to this point that transmission losses, we got this equation summation over m summation over n pm bmn and pn. So we got this equation. From this what we can conclude is the power loss, we can have this in terms of the power outputs of the generator. Okay, this pm is the power output of mth generator and Pn is the power output of nth generator. So power output is nothing but it is a function of power generation or the power output of the generators. Okay, and here this Bmn, it is called as loss coefficient, or it is also called as simply B coefficient. Okay, and the unit for this is B is, it is megawatt inverse. Okay, or 1 upon megawatt. So now let us have this discussion on this. See, when we have to consider the transmission line losses and when it is to be neglected, that is very important. We are doing these studies in order to have in order to get the minimum possible operating cost. Okay, so for this it is very important to know the cases or the situations where we can neglect the transmission line losses, because if we include this will make our calculations very complicated. Okay, so we do have some options there we can neglect these transmission losses. Okay, so what are the conditions? If transmission line transmission line is short line. Okay, if it is a short transmission line, or load density is very low, load density is very high. Okay, it is not for very low. If the load density is very high, or if the transmission line length is very short, in that case we can neglect, PL can be neglected. Why we can do that? Because if the transmission line is small, or if it is a short transmission line, then definitely power loss will be there, but comparatively it will be very less. So if it is a very small value, then we can neglect it. Better to neglect it. Okay, or if the load density is very high. Okay, see, what is the ultimate aim here regarding the generation, that the power demand plus power loss, it should be equal to power output of all the generators. Okay, this is what actually expected. uh, we should satisfy this constraint. If you see here, if the power density, if this PD is very high, okay, if it is very high compared to this power loss, then in that case, when it will be high, when the load density is very high. Okay, in that case, this PD plus PL, we can approximate it to PD. Okay, there we can neglect the power losses. So these are the two conditions where we can neglect the power loss. And simultaneously we do have two conditions where we should not neglect the power loss. The first one is if transmission line is medium or long transmission line. If we have, in that case, we should not neglect the losses, we should consider the losses. The second condition, it says, or load density if it is low. load density is low. In these two conditions, we should not neglect the power losses. So I will write here PL power loss should be considered. Okay, now how to consider this power loss? We already know that power loss on the transmission line, it is nothing but summation over m summation over n pm bmn, and this is pn. Okay, so what we can do is we can approximate this power loss as a coordinate as a quadratic function of the power output of the generator. Okay, as we have already seen in previous discussion, if we have two number of generator, then this pl we can write it as p1 b11 p1. Okay, put m and n both as one. Okay, now let's keep m as 1 and n as 2, so we'll get pm p1 b12 p2. Okay, now let's make m as 2 and n as 1. In that case we get p2 b21 p1, and the last term make m and n both as 2, so we'll get p2 b22 again p2. If I make if I simplify this p1 p1, it will become p1 square b11 plus, you see here this b12 and b21 both are nothing but same. Okay, so let me write here as a comment, b12 is same as b21. Okay, so in that case, since b12 and b21 as both are coming same, and this is p1 p2, this is also p1 p2, so we can have here 2 into p1 p2 b12. Okay, again the last term you see p2 p2 square, and this is b22. So this way we can write the power loss equation for any number of generator. Okay, here we have considered only two generators we have, so for this we will get this type of quadratic equation. Okay, so this is how we can include the, or we can consider the power loss. Okay, now what is the objective here? Why we are studying this? Because we want to have the optimum generation scheduling. Okay, what is the aim of optimum generation scheduling? What is the objective? The objective is to minimize the total operating cost. Okay, I want to minimize CT. What is CT? It is total operating cost. CT is nothing but C1 plus C2 plus C3. This way it goes up to Cn. Okay, next is we should we do have some physical limitation, so we should write that as a constraint. Okay, while getting or while solving this for to get the minimum from of this value, we should satisfy certain constraints. So what constraint we should satisfy here? The constraints are, see here it is very important. The first constraint, which is power balance equation or equality constraint. Now there is a slight modification here. What modification we will have? Previously we were writing only power demand should be equal to power output of all the generators in our previous discussion, where we have not considered the transmission losses. But as we are considering, so we should have here PD plus PL, it should be equal to power output of all the generators. Okay, it should be equal to power output of all the generators. So this is the power balance equation. This is called as power balance equation or equality constraint. The next constraint that we can apply is inequality constraint. Okay, so that inequality constraints are nothing but same way. Pi minimum should be greater than or equal to Pi should be less than or equal to Pi max. Okay, this is inequality constraint. Inequality constraint, or if you can call it as generator limit or power generation limit. Power generation limits. So we should, while solving this problem, we should satisfy these two constraints. Okay. Of course, we know how we can get the maximum of the total operating cost. For that, definitely we will take the help of that Lagrangian multiplier method. So I'm going with that method, Lagrangian multiplier method that I'm going to use here. So as per that equation, that as per this Lagrangian multiplier method, it says define a function, okay, and that function will be total cost plus this lambda, that is Lagrangian multiplier, into, now earlier we used to write here PD only, now I'll write PD plus PL minus P1 plus P2 up to Pn. Okay, so this is, let us call this as equation number 1. So now what is our objective? We have to solve this equation, we have to solve this Lagrangian equation to get the minimum of this total operating cost. And to solve this, we have that KT conditions, that are nothing but Kuhn-Tukur conditions. KT conditions to get minimum of equation 1. So what are those conditions? It says that the first condition is differentiation of this Lagrangian function with respect to power output of ith generator, it should be equal to 0. Again, one more term, it says the differentiation of this Lagrangian function with respect to that Lagrangian multiplier, it should be equal to 0. Okay, so we have to use these two conditions to get the minimum of this equation number 1. Okay, so let us apply this. I'm going to apply the first condition. As per this first condition, differentiation of this Lagrangian with respect to power output. Let's see what we will get here. See here, it is the first term in this L, it is CT. CT is nothing but P1, C1 plus C2 plus C3 plus C4 up to Cn. So somewhere we will have that Ci term because we are differentiating with Pi. Na? So in this CT, we will definitely have that Ci term. And we know that this cost, it depends on the power output of the generator. So definitely the one term, this CT is nothing but it is a summation. In that summation, definitely one term will be there, which will be the function of this Pi. So for that, I can write Ci with respect to Pi. We got the first term plus, here you see in this bracket from P1 to Pn, somewhere we will have that Pi term. Okay, somewhere we will have that Pi term. Again, in this power loss, just now we have discussed the power loss formula. Power loss is nothing but it is a quadratic function in terms of the power output of the generators. So definitely this PL will also consist of that Pi. Okay, so for that we can write it as, first we will keep this lambda as it is. So lambda into this term, differentiation of this power loss with respect to power output, and this term, it will be with negative sign, minus, see we are going to directly differentiate that variable. So differentiation of that variable with respect to itself will be 1. So we'll get directly lambda here and it should be equal to 0. Just rewrite these terms. Just rewrite this. You will get differentiation of Ci with respect to Pi. Okay, make this lambda as common. Take this lambda as common. Lambda into, will get 1. Okay, better to, before we take lambda as common, better we shift this terms on that side first. Okay, if we shift on that side and if I take lambda as common, so I'll get 1 minus this differentiation of power loss with respect to power output. Okay, now here you see we are coming across a new term here. Okay, we know this differentiation of cost with respect to power output, it is nothing but incremental fuel cost. Okay, and the physical meaning for that is if we want to increase the generation by certain amount, how much money we have to how much increase will be there in the total operating cost that will be give that we can take with the help of that incremental fuel cost. Same way, see here, it is the power loss, differentiation of power loss with respect to power output. See, we can read this in this way. What will be the change in power loss for change in power output? PI is nothing but the power output of the generator. Let us assume that this dow is nothing but a small change. For small change in power output, what will be the small change in the power loss? So from this, we can consider this fraction as incremental loss. Okay, we can consider it as incremental loss. Okay, incremental loss or incremental transmission loss. Better we write incremental transmission loss. So what is the meaning here? If suppose if I'm going to increase the output of the generator, definitely loss on the transmission line will increase. By what rate it is going to increase, that will be that we can understand from this fraction. Okay. Now let us call this as equation number. We have already taken equation 1, so let us give this as equation number 2. Okay. So this equation number 2, I'm going to further expand this. I'm writing this as a differentiation of Ci with respect to Pi. Okay, it is lambda minus lambda into PL divided by Pi. Okay, with respect to Pi. So now what we can do here, let's keep this lambda in the bracket only. Okay, because this we have already derived. Okay, so now I'm going to write this as this lambda, that is the Lagrangian multiplier. This bracket will go in the denominator here. Okay, so instead of writing in denominator, I'm going to write this in this way: 1 upon 1 minus dou PL by dou PI, that is power output of the differentiation of the power loss with respect to the power output of the generator, into this dou Ci divided with respect to power output of the generator. Okay. Now you see here, I'm going to define one term for this. Okay. Now I'm going to write here as lambda is equal to Li into dou Ci, or differentiation of Ci with respect to Pi, where this L is called as, it is nothing but, first we'll write here, it is 1 upon 1 minus L, it is 1 upon 1 minus power loss, differentiation of power loss with respect to power output, and this term is nothing but penalty factor. This term is nothing but penalty factor. Okay, so let me rewrite this term once again. So this lambda is coming equal to Li into differentiation of this cost with respect to power output. Earlier, when we have not included the transmission losses, there we got this lambda is equal to simply differentiation of the cost with respect to power output. Now we are getting an additional term called penalty factor here. We are getting one additional term called penalty factor. So this transmission losses in the calculations, this penalty factor is representing that transmission losses. Okay, or else we can say that penalty factor, it represent penalty factor represent transmission line loss. Okay, it represent the effect of transmission line loss in the calculation. Okay, so now what we can say, it is generalized. If we are writing for the first alternator or the first unit, we will have this term as, see, if we have number of alternators, so in that case we will get this as L1 differentiation of the cost function of the first unit with respect to power output of the first unit. Okay, similarly for second unit we will have this term. Same way, for nth unit we will have this term, and all these terms are equal to each other, and it is nothing but the Lagrangian multiplier. Again, it is lambda. So you see here, please keep this point in the mind. This function, this equation, let me give the equation number as well. We have given equation number 3. 2 we have used, we'll give it as equation number 3. So it is called as exact coordinate equation. So what is your understanding from equation number 3? The equation number 3 says that in order to have the optimum generation scheduling, earlier what we used to do, we used to make the incremental fuel cost of all the generators as same. But here what we have to do is we have to multiply the incremental fuel cost. We have to multiply this incremental fuel cost with its respective penalty factor. Okay, and whatever term we will get, this term should have the same value as lambda. Okay, for all the unit it should have the same value. If we are doing so, then only whatever scheduling we will have, that scheduling will be the most economical scheduling. Okay, so you can understand this way. Now how to solve the numericals? When definitely we may get the question for numerical here, but you see here the equation, the power loss equation that we have to deal with, it is a quadratic equation. Okay, and earlier where we have not included the transmission losses, we don't have that quadratic equation. We had that simple equations, and we solved that simple equation with enumeration method. But when quadratic equation involves, it is better to go with iteration method. Okay, so it is advisable to go for the iteration method. So we will discuss that iterative method here now. Iterative method. Okay, so first step, what you have to do is assume value of lambda. Okay, see how to assume this value of lambda. It is very crucial. One idea I will give you that will help you to assume the value of lambda. See, we have been given the cost function as that alpha plus beta p plus that gamma p square. The cost function is written in this way. Okay, so here what you do is you just see how many units are given, and in each unit you just look at the value of that beta. Okay, and make sure that this lambda should be greater than these betas. Okay, if we have been given some number of generator, compare or take the values of betas from all those generators equation, and just see which beta is having the highest value, and then from that what you do is assume the value of lambda just slight greater than that highest beta. Okay, this will help you to get the or to assume the value of the lambda. Okay, once you assume the value of the lambda, then what you have to do is the second equation, the second step is calculate the power output of each unit. Calculate the power output of each unit. Okay, so you just see here, you have to use this formula. Okay, I'm going to give you directly the formula because we will not deal with that derivation. It is very complicated and it is very lengthy, time consuming. So better you directly take the formula. So that formula, it says power output in the kth iteration, it is lambda in the kth iteration minus beta I. See this beta, now I'm not writing it for kth iteration because this beta, it is a fixed value, it is a constant value, it will not change with respect to iteration. Okay, of course lambda we are assuming in initial phase, we will modify this lambda. You will get the clear idea once we finish up these steps. Divided by, it is 2 into gamma I plus lambda in the kth iteration into bii. Okay, don't get confused between this beta and bii. Okay, you can remember in this way, the better way the difference is, this b will be having in the suffix two numbers and beta will have only one number in the suffix. Okay, so with this equation you have to calculate the power output of the each unit. Okay, once you calculate the power output of the each unit, then what you have to do is you have to see every iteration. When we are going for the iterative method, we should give the condition for convergence, because if we don't give the condition for convergence, then there will be a question mark where to stop, or after how many iteration do we have to stop. So it is better to always give the condition for convergence. Okay, so next what you have to do is check for convergence. Okay, check for convergence means whatever condition now I'm going to state, if suppose if that condition is being satisfied, then we can say that we got the solution and we can stop at that iteration. Okay, and that condition is you have to check that change in power in the kth iteration. You have to check how it will be. It will be pd plus power loss in the kth iteration. See, again I'm writing power loss in the kth iteration. Why I'm writing it so? Because you see, power loss we have written it in terms of the power output of the generator, and here you see power output of the generator is changing with respect to iteration. So as power output value changes, power loss will change. Okay, so that change in power, it is what you have to do is you have to check this minus p1 in the kth iteration plus p2 in the kth iteration up to pn in the kth iteration. Okay, so you have to check for this. Okay, if suppose if this change in p, if that change in real power, or the difference between this pd plus pl with respect to the power output of each generating unit, if it is within the specified range, then we can stop the iteration. If it is not, then we can repeat the iteration. Okay, this will be specified in the numerical. Okay, if you are going for the numerical, this will be specified. Or else, if suppose if you are doing the study on your own, then what you have to do is, based on the accuracy level you are expecting, you can set this range for this. Okay, you can decide and you can set the range for this. Okay, if suppose if you find that this difference is, you are getting a big number here, you are not getting a very slight number. So always we expect, see, this is nothing but the power demand plus power loss. This is what we have requirement. Okay, this is what our requirement is, and this is what our output is. Okay, if we come very close to the requirement, then we can say we got the solution. If suppose we have not got, if we are not very close to the requirement, then what we can say is we are not close to the solution, we have to go for next iteration. Okay, if it is the case, then we can go for next iteration. If above condition is not satisfied, go for next iteration. So when you will be asked to go for the next iteration, so for that what you need to do is you need to calculate change in lambda. You need to calculate change in lambda in the kth iteration, and it is the change in lambda in the kth iteration. It is simply change in p in the kth iteration that uh, you have already calculated here. Denominator you have that summation, uh, change in differentiation of this power loss with respect to lambda. Okay, you have to check for this. Okay, again this will be having different value in different iterations. Okay, so this way you have to check for. Okay, differentiation of the power output of each unit with respect to lambda you have to check, and you have to calculate this, and you have to get this change in lambda. Okay, once you get this change in lambda, we have to modify the lambda value. Okay, so how we can modify the lambda value, as we are going for next iteration it will start with put k as now k plus 1. So what lambda we will get in the next iteration, lambda in the next iteration it will be lambda in the previous iteration plus this change in lambda in the previous iteration. So this addition will give us the new value of the lambda. Okay, once we get the new value of the lambda, we have to repeat the step 2 and 3. Okay, we have to go for step 2 onward. Okay, repeat step 2 and 3. What you have to do is, once we get the new value of the lambda, again calculate the power output of the each unit. After calculating the power output of each unit, check for this convergence condition. If it is satisfying, it is okay. If it is not satisfying, calculate the change in lambda. How do we calculate that? That I have already given to you. Once you calculate that, you just check if it is within the specified limit. It is okay. You can stop your iteration. If it is not, you have to go for next iteration. Okay, and again how to go for the next iteration, that is also been given to you. Now one more thing I must give you here, that denominator term, the differentiation of the power output with respect to the lambda, you can calculate this as summation. Here summation is given, I is equal to 1 to ng, the differentiation of power output of ith unit with respect to lambda in the kth iteration. You will get it as, first let's write this summation I over I is equal to 1 to ng. Okay, now this differentiation of the power output with respect to lambda, here we have to write considering the power loss equation. Okay, so directly I'll give you the terms what we will get here. We will get lambda I, gamma I plus b I into beta I divided by 2 into gamma plus lambda in the kth iteration. Okay, because we are solving it, we are finding it for kth iteration, so definitely we'll use lambda value in the kth iteration into b11 bracket square. Okay, so you can use this to calculate the change in lambda. Once we get the change in lambda, modify the value of lambda, again go for step number 2, step number 3, step number 4. This way you can continue this and you will get the optimum generation scheduling from this way. Okay, thank you very much.